everybody, welcome back. Today we're going to do, let me slide this over and see this a little better. Okay, today I want to do just a basic introduction to electronics, okay? A lot of technicians I've worked with over the years, been doing this 4, 5, 6, 7, 8 years. They do brakes and oil changes. They could pull a motor in and out. They don't understand electronics at all. So I want to just give you a little basic introductory to electronics, okay? So we're going to start out. I got a 12 volt battery here. All right, we're gonna have a positive and we're gonna have a negative side. Okay. And we're gonna use a shift solenoid today because transmission technician, they're familiar, but you can use a bulb. I might even do a bulb in here just to explain it to you. But basically, with any system, we're gonna let's put a fuse in here too. Okay, there's a fuse in there. It's not a great drawing of a fuse, but we're going to put it in there. So, what electronics, the electrons in a battery, they want to complete a circuit. They're always moving. They're trying to get to the negative ones. They're trying to get over here. I'm not going to get into how electricity actually runs backwards. You can watch some really good electronic videos on that, but for common knowledge, we think positive to negative is how electricity runs. So we've got a 12 volt battery. We want to get the electrons to move in a circuit from here to here. You can't just connect a wire like this because you're going to blow the battery up. It's going to melt the wire and everything. There's a thing called Ohm's law, which resistance, voltage equals amperage. If you have 12 volts and 0 ohms of resistance, you're going to have like an infinite number of amperage and it's going to melt whatever's connecting them to. If you ever crossed a wrench across the battery and sparks fly, that's why. You've got to have some sort of resistance to limit the amperage going through it so you don't fry anything. So we're going to put a fuse in here. We'll determine what size that is in a minute once we figure out our load. Okay, so we're going to run power out of the battery. It's going to go into the fuse, out the other side, into the shift solenoid. Okay, like I said, we can use a bulb, and I'll probably do that next just so you can understand. And then we've got a ground side. Okay. So on the ground, we're going to run that up, and that just goes here. You don't need a fuse on the ground side. It's just a return path after the load is spent. It can make it back to the electrons, travel back, okay? Now, we're going to want to actually put some sort of switch in here. I'm going to take this out, because right now, if this was the case, the sun would be on all the time, and that's kind of useless. We need a switch, okay? So, we'll put a little switch in here. And how this works is you have a switch that can go this way. Let me get the little draw in here. Power's going to come into this pole and then that pole. So right now, the little switch is off. It needs the switch up to connect it. So right now the system's off, and there'll usually be a computer and external source that'll control a switch. We're not gonna get too deep into that. We're just gonna keep it simple. 12 volts, running a solenoid, okay? Power's gonna come up to a switch. You have to flip the switch, which then this flips up to here. Now it's gonna connect it there instead of there. It's gonna go that, through a fuse, to there. Now, you've got 12 volts coming in a solenoid, and inside a solenoid, there is a whole bunch of coils of wires, okay? It goes through the coils, creates a magnetic field, which then actuates the solenoid. And then, after the load is spent, comes back out. Now, we want to determine how many amps this fuse needs to be so the system works. Let's say we have a 12 volt supply, which we do. We have 4 ohm resistance on this coil. If you were to put your ohm meter on there, you test from here to here with it unhooked, you would see the system will say the solenoid has 4 ohms worth of resistance. If you check just a piece of wire, you'll see most time it's 0 ohms. There's no resistance on it. This coil is coiled so many times, actually creates resistance in there. And with the magnetic field, that's what's going to apply. You've got 4 ohms resistance. You got 12 volt battery, Ohm's law. You're going to take 12 volts, divide that by 4 ohms, you're going to end up with 3 amps of resistance. Okay? So the system normally when it's on is going to draw 3 amps. So you can over here put a 5 amp fuse or a 10 amp. You don't want to go too much because if this starts to have a problem, and you don't want it to go too high before it burns out. You don't want to put a 50 amp fuse in there. So we're going to say that comfortably could have a 5 amp fuse and we're okay. All right. Well, how do fuses blow and why? Let's say this winding inside shorts out. All right. Melts across your power and ground. You got a short directly from here to here. Now it's short means short of the ground. You got something melted across there. It no longer goes through the coil. It has a direct path. The voltage can go from the positive through the switch, through the fuse, and back. Right now you have very little resistance in that circuit. Practically 0. So if you were to divide 12 volts by 0 ohms, 12 divided by 0, you're going to have a crap ton of amperage going through there, and it's going to fry the system, fry the wire. So we know we're going to have much higher than 5 amps. We're going to have like a very, very high number. That right there, I mean, the amperage of the battery, I think 500-600 cold cranking amps. So it's going to hit that certain point. But once you get above the 5 amps, it's going to burn that fuse out. That's the purpose of it. Now you've got an open system. Now it's shorted here, but now it's an open system because you have a break in the fuse. So power can no longer go through. And now you've got an open solenoid. Doesn't work. Computer tries to command the switch with the wire. Nothing happens because you've got it burn out there. Okay. We can do the same thing with a light bulb. So you're not worried about on and off solenoids. We'll just do this. Same scenario. Very basic. Have a light bulb. 2 pins. And I like to draw it this way. You're going to have coming in, and it's going to coil back down. Okay. Same scenario. You're going to put a little switch in here and some sort of fuse. And that's the switch. You get your power coming to the switch, and it needs to go to here. You've got your ground side on the other side of the light bulb just for the return path. And what you're going to have, let's just say when we turn the switch on, this connects, okay? When the switch is off, it flips down, and it would be down here, it would be an open circuit. So the light's going to come on. We got power going through the switch, which we've turned on with like our headlight switch or turn signal. Comes through, goes through its fuse to the load, it's spent, and back down. Same thing. If we determine the resistance on a light bulb, I don't know, we'll say this one's got 12 ohms of resistance. We got 12 volts. You're going to draw about 1 amp. It says lamp. Didn't intend that, but that's cool. So you got 1 amp going through there. So if you were to take your voltmeter and unplug or test on each side of this, or like disconnect it, and you were to test here and here, put it between your voltmeter now, make sure it's on the right setting for amperage. Here to here, you're going to see a 1 amp draw, okay? You will be able to test that to make sure you have the proper amperage. You can actually ohm out your bulb, know you have a 12 volt supply, and determine how many amps that's supposed to draw. And once again, with this system, if you have a break in the ground, guess what? No return circuit, you got no power. It has to be able to complete the circuit for it to work. Just because the power comes in isn't going to work if it can't complete the circuit, okay? A lot of people think, oh, I've got power in, it should light up. That's not how electricity works. It has to finish its circuit to work. Otherwise, it's just dead in the water. Nothing happens. All right, so that would be an open. You have a break over here. That's an open. And shorts, like I said earlier, a short is this. Let's say we got a wire harness rubbing. and it actually bumps a ground right here. Now, electricity is going to take the path of least resistance. It's not going to go backward. It's basically going to go from here directly right to the ground. This is going to get super hot. It's going to probably burn off the wire because it's shorted before the fuse. If it's shorted after the fuse, up in here, like across here, come out here and it actually shorted across there, that fuse would pop first. If it shorts before the fuse, it's going to go right over here and it's going to burn out possibly a switch if it's before the switch, if it's after the switch, which is a good way to determine where you have a short. All right, because you can test for power on each side, or if your switch is melted, typically it didn't make it to the fuse, it shorted before the fuse. There's different ways to determine a short based on your symptoms and where you want to test. But like I said, if a fuse is blown, typically your short to ground is after the fuse. If the fuse isn't blown, but you've got no power there, but you know there's a short, typically a switch might be melted out, or a harness somewhere is completely destroyed because it shorted directly before it ever had a chance and it fried the wire and it burned out. So those are some tips on how to figure out where your short is. An open, a little more difficult to find, but you pretty much just trace it. You can check up here. If you have an open right here, you got no power at the bulb, go back to your fuse. If you got power on both sides, then you know the open is broke between the load and the fuse. All right, if you have no bulb, you do the same thing. Check for power at the switch with the switch on. You got power coming out, then you know between that and the fuse is the problem. And vice versa. Power coming into the switch. If you don't have it, then obviously you got nothing. So that's how you can kind of narrow down where you want to look and jump to a spot sooner than having to check the whole system, okay? And kind of work your way back or use some knowledge and say, oh, you know, the fuse isn't even blown. I've got no part of the fuse. I've got a switch problem or a supply problem from a PDC, stuff like that. All right. So that's just a basic introductory to electricity, how they work through a load, whether it's a solenoid, a light bulb. They all work the same way. Even linear solenoids, pulse width modulation solenoids, PWM. They're controlled powers and grounds by the computer, but the process, whether it's coming from the battery or the computer, is still the same. It needs power and a ground for an electrical circuit to work. A cluster has a power and ground. Everything, just like your computer or anything you plug in at home, is power and ground. Anything electrical needs power and ground to work. And we just have fuses in there to protect the circuits. We have switches, and we have relays, and there's a reason for relays, which I'll do videos on. But that's just a basic intro to electronics. So I'll see you next time. Thanks for watching RZ Auto Solutions. I'm Mike.